Okay, this is part 2 of section 3.1. We're going to go ahead and continue on with an example. In these three examples, we're going to go ahead and sketch and describe the transformations that are happening to these exponential functions. Okay, so let's start off with letter A. We have 4 to the power of x minus 2. The transformations work pretty much the same as they've always have. So think of this as like your h value, okay? And since it's part of the x, you can think of it as an opposite, which means that the graph is going to be moving 2 spaces to the right, okay? So I want to go ahead and write that down first. I'm going to shift horizontally or translate, okay, 2 units right. So 2 spaces to the right, because it's a minus 2, so it's actually going to go the other way. So when I graph that, the way I'm going to do that, because it's a little bit tricky with the exponentials, we don't want to do a whole bunch of tables, right? So what we're going to do is we're just going to graph our original function. In this case, think of our OG, remember our original graph, as y equals 4 to the x. So think of that as our parent function for this one, which means that we're still going through 0, 1. Okay, but the rate is now 4, so you can think of it like 1, and then it would be up at 4. So let's pretend. I'm gonna kind of estimate here. 1, 2, 3. So somewhere up here. Okay. So this graph might look something like this. Okay. Okay, so this would be kind of like our 4. And all we're going to do is we're going to move these 2 spots that we have at least 2 units to the right. So let's go ahead and do that. Let me add some more marks here. So let's say this is 1, so -1, -2, -3. And I'm just, like I said, this is just a sketch. So this point is now going to jump 2 units to, oh, actually, we're going the other way. I'm sorry. 2, 3, 4. So we're going to go 2 spaces over. So 1, 2. So there's my new space, or I should say point right here. This one's also going to go 2 spaces over. So 1, 2, maybe somewhere right there. So this point would now be 2, 1. And this one's going to be 1, 2. I think I went a little too far. Should be 3, 4. Okay, so the original ones were 0, 1, and this was 1, 4. By the way, the reason I know that this is at 1, 4 is because since my base is 4, that means that the rate of exponential growth here is by 4. So for my first space here would be at 4. Okay, but anyway, this would be my new graph here. I have 2 spaces to the right. So I'm going to go ahead and just connect that here. And that is basically it. That's all you got to do for these. Give me a rough sketch of what it'll look like. Okay. All right, let's try another one. So for letter B, we have h of x is equal to 4 to the x plus 3. So think of this as your k value now. Remember that the k value makes the graph go up or down. So let me go ahead and let me separate this just a little bit here. This one won't be as difficult because up or down is a little bit easier to monitor. So I know that this one is going to go 3 units up. Okay, so same deal. We're going to go ahead and do our original graph here, which was, again, this one, the 4 to the x. So we have a point at 0, 1. We have a point at 1, 2, 3, 4. I probably should have done that one a little bit up. That's all right. So this is our second point at 1, 4. I know this graph does something like this. Okay, again, this is our OG, our parent function for this one. And if I'm going to go 3 spaces up, I'm going to move these 3 points up by 3. So I'm going to have to estimate one of them because I didn't really put space. So 1, 2, 3. So this one's up here now at 0, 3. And this one's going to be somewhere up here, which I'm out of space. It's going to go up by 3. So it would probably be up here 1, 7 or something like that. Sorry about the bad graph. So this might do something like that. Okay, something like of that sort. And that's basically it. So make sure when you do your graph, you do give yourself enough space. I probably should have done minus instead of positive to make it go down, but that's all right. Okay, so that's basically it for that one. We have one more. This is going to have a negative exponent. So that means the graph, instead of going this way, it's going to go the other way. It's going to be decreasing. Okay, so let's go ahead and do our sketch for this one. But before we do that, let's describe the transformations. So we have this negative x. We can think of it as a reflection because it's negative, but we can also just use the OG. We can make our OG y equals 4 to the negative x because we know what that one looks like. Okay, so if we use this one, then we should know that it's going to be going the other way. Okay, so the only thing I'm going to focus on really is this negative 3, which means 3 units down. And the good thing about these is you can always graph them and check them out. Okay, so let's go ahead and do our original function here. So we have, again, 0, 1. This time, instead of the point being over here at 1, 4, so 1, 2, 3, 4, instead of being over here, it's going to be on the other side, right? Because it's going negative. So now we have negative 1, 4. So my original graph is something like, didn't draw this one too great either. I'm not great at drawing simple things, guys, sorry. So it's something like this. Okay, and the only thing I did is I'm going to move it down by 3. So let's go ahead and do that. So this point, get a different color. This point's going to go down by 3. So 1, 2, 3. So now it's going to land on 0, negative 2. And this one's also going to go down by 3. So 1, 2, 3. So now it's here at negative 1, 1. And it's something like the following. Okay. One thing I did not notice, or I did not mention, I probably should have. We can kind of tell where this is going to get close to based off of our k value. So the k value actually helps us out with our horizontal asymptote. So in addition to this, I also know that I'm going to have a horizontal asymptote here at negative 3. So originally my horizontal asymptote was at 0. So now that the graph went down by 3, it also went down by 3. Okay, and same thing with the ones up here. So just really quickly, letter B. Okay, this one went up by 3. So my original horizontal asymptote was at 0. Now it's going to be at 3. And this is just kind of extra, but you might need it for another part of your homework. Okay. All right, moving on. We're almost done. This is going to be a short video. We have a lot of stuff to copy here, mostly just information. Okay, so we have this thing called the natural base E, okay, and this is kind of a special graph. So the base is not really a number that a real number. Well, it is a real number, but it's not one that we're familiar with. It's this number E, which is 2.7182182, and it just kind of keeps going. And it looks like this: f of x is equal to e to the x. And this is just, it's called the natural exponential function. Okay, they like to use it a lot in calculus. Here's what it looks like. Okay, so you can see that it follows the same pattern as a increasing exponential function, and the points that we have here are just denoted by the x value, and then the y value is whatever that value is equal to here. Okay, so just really quick, some calculator practice for this. For this one, you might have to use a probably your graphing calculator for this one. Let me see. Give me a second. Let me see if a regular calculator has it. All right, so it looks like mine does have it. If yours doesn't have it, if yours doesn't have this little e to the x, let me focus that a bit. If you don't have this e to the x, then you might have to use another calculator, okay? But basically, you just press it and plug in the number that you're looking for. So in this case, the first one is negative 2. So negative 2, close the parentheses, and there it is, 0.135335. So this is approximately 0.135 3, 3. I'll just leave it like that, 3, 3, 5. The next one, well, you do the same thing, but you put in the next number. So I'm getting this value, 0.3678, 0.3678, and the last one, 0.25. Here's what it looks like. Okay, 1.284. So, just basic calculator skills, nothing too fancy here. Okay, you will notice that some of them might be undefined. So for example, if I wanted to find, actually, no, I'm sorry, not for this one. For this one, we're good to go. I'm thinking of a different function. Yeah, that's basically it for this next part, and we're almost done. See, I told you this video wouldn't be too bad. We have some applications here, and this is also something that you should be familiar with. The one we're going to talk about here is compound interest. And there's two different ones we're going to see. We're going to see n compoundings per year. So in other words, if you're adding more money or taking away money, so many times per year, and then continuous compounding, which is just constant. Okay, or not? I shouldn't say well. I guess I can say constant. So the way it works is we have after so many years, the balance of whatever amount of money you have there or owe in the account, starting with the amount you started with. So either the amount that they loaned you or the amount that you put into your savings, and an annual interest rate. This does have to be in decimal form. So please make sure that this part right here does have to be in decimal form. Usually they'll give you a percent and you have to change it to a decimal. And these are the formulas we're going to use. So if you're going to be using the n compoundings per year, we use this formula, p times 1 plus r over n to the n times t power. If you're going to do continuous, we're going to use our little e number here, okay? Our natural number e. Or I'm sorry, I should say natural number, our natural base e, my bad, natural base e. So let's go ahead and just jump right into an example. Like I said, these are pretty simple. Here we have you invest $6,000 at an annual rate of 4%. Find the balance after 7 years for each type of compounding. And then we have some words here, quarterly, monthly, and continuously, or continuous. Couple things here. We want to go ahead and identify what everything is. So if this is the amount that you invested, this is how much you started off with. That's going to be our P, our principal amount. Okay. The annual rate of 4%, this is going to be our R, but remember that we have to change it to a decimal. So this is going to be 0.04. You just take the number, the decimal, and move it over 2 spaces to the left. Okay. And then the balance after 7 years, that would be our time. So this is going to be our T. So what we're looking for, we want to find the balance. That's we're looking for A. Okay, we want to know what is A equal to. So let's go ahead and look at each one of these, and we're just going to decide what these things are now. If we're looking at quarterly or monthly, this is talking about the N, the number of times compounded. So quarterly means, every quarter of the year. So we're just going to divide 12 by 4, which would be, 4, N equals 4, okay, every fourth time in the year. Monthly would be 12, okay, because there's 12 months in a year. And then continuous is going to be that second one. So this is going to be the A equals PE, and then R to the R times T power. I can't say that. So this one I just remember as PERT. Continuous flow is going to be PERT. Let's go ahead and try this. So all we have to do really is plug everything in. So A equals, okay, we start with our principal amount. So $6,000 times 1 plus the rate, so 0.04, over the number of times compounded, so 4, to the power of nt, so 4 times 7. And again, I'm just getting this formula from the page before. Okay, for the second one, A equals, again, 6,000. So it's basically this one again, but now we're going to do n equals 12. So 1 plus 0.04 divided by 12 to the power of 12 times 7. And last but not least, A equals 6,000 times E to the power of our rate, so 0.04 times 7, because that's the number of years. So let me go ahead and just get that real quick for you on the calculator. By the way, I would use probably a Desmos or the other one for this one. Okay, so I went ahead and did these on my phone really quickly. You can see the first one is right there. Just a quick tip, if you use Desmos, when you do the power button here, you want to put that 7 in parentheses at the times. Otherwise, it'll bump the 7 down. But we got 79, so 79.27 and about 75 cents. Okay, for that one. For the second one, we're doing the same thing, but now we're going to plug in a 12 instead. So you can see I put a 12 for that one. This one came out to 7935.08. Okay, and the last one, the continuous one, if you're going to use Desmos for the E, you want to use your letters because the E is not really in there. I kind of had to look for it. Just type in E and it should come out. This one is 79.38 and 78 cents. Okay, so just a quick comparison. If you were to do this, you can see that out of these three cases, it looks like this one is the one that pays the most money. And in general, you'll see that the continuous compounding usually does offer more money. Okay, but yeah, guys, that's basically it for this video. If you have any questions, as always, let me know.